Look at this visualization of a digital container overflowing with geometric shapes. It illustrates a mathematical ceiling that every developer hits when working with AI coding assistants over long periods. Every prompt, code snippet, and debugging session gets logged directly into the LLM's context window. The context window is the temporary working memory the AI uses to process and understand your current task. As continuous interaction logs pile up in that space, the ratio of useful signal to useless noise plummets. You start seeing immediate engineering symptoms. The system's retrieval recall drops, response latency spikes. Soon you find yourself repeatedly prompting the agent with the exact same architectural guidelines you established days ago. It becomes a classic needle-in-a-haystack problem of long-term AI memory graph management. The agent has your structural decisions stored somewhere in its massive memory, but it cannot isolate that one critical variable out of the thousands of lines of surrounding chatter. Without a mechanism to aggressively drop transient data, like minor syntax errors or abandoned debugging paths, a persistent agent inevitably suffocates under the weight of its own historical logs. Anthropic recently rolled out a silent experimental update to their Claude Code environment to solve this exact bottleneck. They call it AutoDream. AutoDream functions as an asynchronous garbage collection and synthesis layer. Garbage collection is a standard computing process that automatically frees up memory space by deleting data no longer in use, but here it is applied directly to the AI's cognitive state. This split-screen logic model shows how the feature mimics biological sleep. On the left, the wake phase handles real-time inference, fast linear inputs and outputs while you code. On the right, the sleep phase operates as a cyclical, background batch processing loop. During this downtime, the system ingests the raw, chaotic interaction logs from your wake sessions and compacts them down into highly dense, indexed markdown files. This shifts the developer's focus. Instead of meticulously trying to curate what the AI records in the moment, you rely on the system to actively manage its own cognitive load in the background. To see how the system mathematically bounds context size over time, we examine Claude Code's three-tier architecture. The baseline layer is the active session, optimized purely for high-speed coding and debugging flow. Sitting directly above that is the intermediate layer, auto memory. This operates independently as a continuous, append-only log of your interactions. Auto memory automatically records your project context and structural decisions into raw.mmd files. These are specific memory markdown files designated for storing the AI's running structural knowledge base. Operating Layer 2 in isolation creates a fatal flaw. Append-heavy processes that never delete anything inevitably generate massive, bloated context files. Because these files are injected into every new prompt you make, all those excess unpruned tokens flood right back into your clean active session, consuming your operational limits. This is why Layer 3 exists. The AutoDream subagent activates at the top level, sweeping down to absorb the bloated data from the memory layer and compacting it instantly. It actively drops transient conversational context and merges duplicate historical entries into single unified rules. By adding this dedicated batch processing tier at the top, the system prevents the raw append-only log from degrading the performance of your daily coding environment. AutoDream is enabled globally across your entire Claude environment, but it heavily isolates its execution and file management on a strict per-project basis. Looking at this dark mode terminal UI, you can see the manual trigger mechanism. You invoke the subagent using a simple natural language command, /dream, and the status line shifts to indicate the process is running. If not triggered manually, the system relies on an autonomous temporal trigger, running a background process every few hours based on elapsed time. Alternatively, it uses a volume-based trigger. Once your active session count crosses a specific threshold, the subagent activates automatically. This background processing scales effortlessly. In heavily active projects, the subagent parses and consolidates hundreds of historical sessions simultaneously within minutes. It operates within strict safety boundaries. The subagent is walled off, only permitted to touch and update specific memory context markdown files. It will never alter your actual codebase or executable scripts. Through these overlapping triggers, the AI self-regulates its own context window, removing the need for the developer to manually monitor token limits. This flowchart maps the exact computational sequence once AutoDream activates. The pipeline starts by gathering all recent session data and reading the current state of your existing memory files. These inputs feed into the core synthesis objective. The subagent is instructed via its system prompt to perform a reflective pass over the collected data. It operates under severe constraints. It must maintain strict line limits and structure the output as a highly organized index. A raw, verbatim data dump is strictly prohibited. This requires actual pruning. In this computational context, pruning does not mean summarizing. It means the active, permanent deletion of redundant or irrelevant context. Verbose, multi-turn conversational logs are entirely discarded. They are replaced with single-line descriptions that link directly to the newly compacted files. Because the rules are strict, the pipeline is highly efficient, requiring minimal background compute time to reorganize massive amounts of session history. Effective AI memory management relies on mathematically optimizing what is kept to ensure high relevance across future sessions. Looking at this side-by-side technical comparison, the physical state of the project files is drastically different. On the left, we have the pre-execution state, a dense block of unstructured text. On the right, the post-execution state is a minimalistic, bulleted markdown index. This highly structured index directly lowers token latency for all future inferences. Token latency is the processing delay caused when an AI evaluates thousands of words per prompt. Fewer words mean much faster response times. The compacted memory also eliminates the friction of starting a new task. You no longer waste your first 3 prompts re-explaining the project architecture to the agent. The system guarantees that the context injected into your new session is almost entirely high-signal data. Reducing the raw data surface area allows the agent to isolate specific project logic without scanning through thousands of irrelevant log lines. The ultimate value of this pipeline is that it transforms a static, dead markdown file into a dynamic, self-healing memory graph. This brings us back to the biomimetic parallel. Human cognition relies on sleep to convert chaotic daily experiences into structured, accessible long-term memory. As autonomous AI agents scale in complexity, they require these exact same dedicated asynchronous cycles to index their own state. Managing the context window has become the primary engineering constraint, scaling in importance alongside the raw intelligence of the model. Because of this, the daily workflow of a developer using AI is shifting. The emphasis is moving away from crafting hyper-complex multi-paragraph prompts. The next phase of AI interaction requires focusing entirely on state engineering and architecture management, building systems that maintain their own clarity. The most capable autonomous agents will be defined by their ability to selectively forget, maintaining a clean, high-performance state as the project grows.